Introduction to System Chain Code. Till now, I have talked about application chain code that is developed by the Hyperledger Fabric developers for defining the behavior of a specific application. In this lecture, you'll learn about a special type of chain code known as the system chain code. This system chain code is part of the peer binary by default, but the integrators can change the system behavior by implementing custom system chain codes. Fabric 2.x support the externalization of the chain code build and chain code launch. Let me explain what that means. Chain code build process in 1.x used to be carried out by the peer by launching a build container. Now that process still works in 2.x, but in addition to the container-based build mechanism, peer also support an external build interface. So what that means is that you can put together your build process in an independent component and then configure the peer to use that independent component to build the chain code. From the launch perspective, the chain code can be launched as a service in any kind of container. For example, you can host your chain code as a process. You can host your chain code in a Kubernetes pod. So it really doesn't matter how you are hosting your chain code, as long as the interface is exposed by the chain code can be configured in the peer. It will be invocable from the peer. Bottom line is that you can use any technology to build the chain code now, because the build process and the hosting process or the launching process is externalized. Please note that if you haven't modified the options for the launch and build of chain code, then the peer will exhibit the same behavior as Fabric 1.x. The application chain code is executed in Docker containers. What that means is that when the chain code is instantiated, the peer launches a Docker container and deploys the chain code in that container. These containers are isolated from each other. In other words, the chain code in one container does not have any knowledge or access to any chain code in other containers. And each of these containers and chain codes are bound to channels. Now let's talk about system chain code. System chain code implements the system behaviors so that it may be replaced by the system integrators. These system chain codes are built as part of the peer binary. Let's dig a little deeper into the system chain code. You already know that the application chain code instantiation leads to the creation of Docker containers with the application chain code. System chain code, on the other hand, is part of the peer process. It's instantiated within the peer process at runtime. The lifecycle rules for the system chain code are very different compared to the application chain code. The system chain code may be upgraded as part of the peer binary upgrade, and there is no endorsement policy or functionality that applies to the system chain code. Calls to the system chain code are in memory. In other words, these calls are not coming through the gRPC services exposed by the peer. As a result, the implementation of system chain code within the peer boundary saves the overheads of the gRPC communication. Let's carry out a side-by-side comparison of system chain code and the application chain code. The system chain code is implemented within the peer process. On the other hand, the application chain code is instantiated in the Docker container that is launched by the peer. System chain code governs the system behavior, whereas the application chain code defines the application behavior. System chain code must be consistent across all peers, and the application chain code must be consistent across all endorsing peers. System chain code is not bound to any channel, whereas the application chain code is bound to a specific channel. System chain code calls are in-memory calls, whereas the application chain code calls are via the gRPC. There are 6 default system chain codes: lifecycle, configuration, query, endorsement, validation, and the last one is the underscore lifecycle, which was introduced in Fabric 2.x. Now, the obvious question you may ask is, what is the difference between lifecycle and underscore lifecycle? The difference is that the chain code lifecycle was managed by the system chain code lifecycle in version 1.x, whereas in version 2.x, the chain code lifecycle is managed by the system chain code underscore lifecycle. You will learn the details about these system chain codes in later lectures. The system chain codes are whitelisted by using the parameters under the system subsection under the chain code section of core.yaml. Each of the system chain codes need to be enabled or disabled independently. Integrators can create custom system chain code. The way it works is that the integrator develops the system chain code in Golang. This system chain code is then compiled into the peer binary, so it becomes part of the peer binary. Another way to create custom system chain code is by way of Golang plugins. The Golang plugin is not compiled into the peer binary but is made available as a shared object or library. Plugin is configured for the peer by way of the core.yaml file. The custom plugins need to be set up under the subsection system plugins, and like the system chain code, the plugins need to be whitelisted under the subsection system. Let's summarize. In this lecture, I provided you an overview of the system chain code and system chain code plugins. The system chain code implements the system behaviors. By default, there are 6 system chain codes. Integrators can develop custom system chain codes. Whitelisting for the system chain code and the custom system chain code need to be carried out under the subsection system under chain code. Plugins that the integrator develops are declared under the system plugins subsection. In the next few lectures, I'll go over the details of these system chain codes.